Again, welcome to Mathematics 164 Precalculus. This is our lecture 5-1, which cover exponential functions. Again, this lecture is in our course textbook, chapter 5-1. So our main objective is to graph exponential functions, also to evaluate exponential functions, and also to model with exponential functions. So we start with exponential functions and graphs. Here we say that equation y equal to 2x is an example of a special group of functions called exponential function. Now, the reason why we call y equal to 2 to the power x as an exponential function, because the exponent is a variable. So now if we have y equal to x squared, that's not an exponential function because the exponent is a value. So always exponential function, the exponent is a variable. So we have exponential function definition here. And here we said that if a is a real number with a greater than 0, so that means a must be a positive value, and also a is not equal to 1, then the function f at x equal to a to the power x is an exponential function with a base a. So the base a should be a positive value, and also it shouldn't be 1, not 1, and it's a positive value. So y equal to 2 to the power x is an exponential function because again, 2 is a positive value and 2 is not 1. So let's start with an example. Here they say we should graph y equal to 10 to the power x. Normally when we are graphing a function, there are normal steps we follow. It doesn't matter what type of graph. And for example, in this case, we can come up with any value of x and we can look for the value of y. So for example, when x is 0, it means y will be 1. When s is 1, y will be 10. When s is 2, y will be 100. S is 3,000, etc. So that's what we did here. First, we set up a table. Then we come up with any x value. So in this case, we start with -3 and we end at +3. And the same thing, we can start with any, maybe I may start with -2 or -5, as far as we can get the shape of the graph. So when s is -3, it means we are going to have 10 to the power -3, which will give us 1 divided by 1,000 or 0.001. Then when s is -2, then it will be 10 to the power 2 because our equation is 10 to the power x. So that will give us 1 over 100. And when s is -1, we get 10 to the power -1, which gives us 1 over 10. When x is 0, 10 to the power 0 will be 1. When s is 1, 10 to the power 1 will be 10. S is 2, 10 to the power 2 will be 100. S is 3, then it will be 10 to the power 3, which will give us 1,000. So now we have some x and y values, and we know every point have 2 coordinates. This is 2 dimension, x and y. So we plot those points, and that will give us the shape here. So always exponential function starts increasing slowly, then all of a sudden it will start increasing exponentially. Actually, that's why it's called exponential function. As the exponent increases, again, the graph y value will be increasing exponentially. Linearly means it will increase constantly. So here we say exponential function of the form f at x equal to c times a at x. This is possible only if c greater than 0 and a also is greater than 1, then we call this exponential function as a growth functions. Because as s increase, f at s will increase because c again is a positive value and a is positive value and not equal to 1, so greater than 1. So again, exponential function of the form f at x equal to c. C again can be any constant value or any value. But if c value is greater than 0, which means it's a positive value, and a is greater than 1, then we have exponential function, but it's a growth function, which means as s increase, f at s will increase exponentially. So this is the graph of exponential growth function. Again, the condition here is that the c value should be positive, a value should be greater than 1. Then we can see as s increase, again, y will increase, or f at s will increase exponentially. And we can get the y-intercept at c, which means when x is 0, the c value. So again, we're going to see an example in a few seconds. So the domain is that all the real numbers, and the range also should be y greater than 0. Y will never be a negative value, since c is a positive value and a is a value greater than, again, 1. Y always will give us a positive result. So let's see an example here. So here we have a $10,000 is invested at 6%. And this is compounded monthly, the interest rate. Then the future value of the investment S after X years is given by the following. So S represents our future investment value of the 10,000. So now we are starting investment with $10,000. So our C value will be 10,000. Then here we have interest rate. So here we get 1.005. Again, there's a reason why we are 1.005. Again, the interest rate should be 6%. That is 5, represent 5%. So this graph, this exponential function, tell us that the initial investment is $10,000, and also the increment is 5%. So we should have 1.005. Then 12 to the power 12 times x. Why? Because the interest rate is compounded monthly. So in 1 year, x is the number of years. So if it's 1 year, then we have 12 months. If it's 2 years, we have 24 months. Based on the question. Again, the question says if $10,000 is invested at 6%, it should be 5%. Compounded monthly, then the future value of the investment S after X years is given by the following. Now, our goal is to find the future value of the investment after 5 years. So we just plug 5 to X here. So here we get the solution here. We give us S equal to 10,000, 1.005, 12 times 5. So using our calculator, we will get roughly $13,488.50. Now, the second question is after 30 years. B said after 30 years. Again, one thing we should notice is 6% should be 5%. That's why we have 1.005 here. So the second value will represent 30 years as 30. Then when we do our calculation finish, we get 60,225.75 cents. So now here they say we should know that the amount after 30 years is significantly more than the amount after 5 years, a result consistent with exponential growth model. So as we said earlier, exponentially, as S increases, the Y will be increasing exponentially. They don't increase in a constant interval, and that will be a linear function. With a linear function, S increase in a constant rate, the same interval. So here we say that there's a special function that occurs frequently in economics and also biology is y equal to e to the power s. It's exponential. Again, biology, for example, a good example would be a bacteria. When we have a bacteria in a closed environment, as time goes on, they may increase exponentially we may have 1 will tend to 2. Now, instead of 2 to 10 to 3, it will be 2 to 4, then 4 to 16 exponentially. Now, we have a special e, which normally, if we use the calculator, it's a constant value 2.71828, etc. So here we say because e is greater than 1, the graph of y equal to ex will have the same basic shape as the growth exponential function. Now we can calculate the y coordinate for points on the graph of this function using a calculator. Again, most calculators will have e to the power x. We have the key. So if I'm going to graph x and y equal to e to the power x, first we pick up any x interval value here, -2 to +2. Now we use our calculator. E raised to the power -2 will give us 0.14. E raised to the power -1 will give us 0.37. And always any exponent, any value raised to the exponent 0 will give us 1. And also e raised to the power 1 will give us the e value, which is 2.72. Then e raised to the power 2 will give us 7.39. Then we can plot the points corresponding. In this case, we have 5 points, so we plot our 5 points and draw the shape. So we also have exponential decay functions. So we saw the growth function. Now let's go to the decay function. Now with the decay function, we can see that y equal to a to the power -x. Still always a must be a value greater than 1. Or more generally, the form of y equal to c to the power c times a to the power x. Always c should be a positive value. And what changes here is the negative. So a to the power -x. Always in the growth function, c is a positive value, a is greater than 1, but our x is also positive. With the decay function, the variable s is negative. So this model, the decay for phenomena, and their graphs have the characteristics and the shape shown in our next box here. So here we can see that the functions at the beginning is increasing, then it decreases exponentially as x increase. So here the function y equal to f at x is equal to c a to the power -x. C again should be a positive value, a should be greater than 1. Or we may have y equal to f at x equal to c b to the power x, but this time our b value should be greater than 0 but less than 1. So decay may give us 2 forms. If a, the base, is a positive value, the exponent should be negative. Or if the exponent is positive value, then the base value should be a value less than 1, but it have to be positive. So greater than 0 and less than 1. And again, we're going to see an example here. Here we say we can examine the similarities and also the differences between the graph of y equal to f at x, which equal to a to the power x, and also those of y equal to m times f at x, and also y equal to f times k at x, and also y equal to f at s plus h, and y equal to f at s plus the constant c. And here m, k, h, and c are constant values. We also can explore this similarity and differences for y equal to f at x, and f at s is a to the power -x. So let's start some example here. We can see the graph here. First, y equal to e to the power x. Again, e is a constant value which is greater than 1. X is positive exponent. So we will surely have a growth function. We will have a growth function. Now, the next we have y equal to negative 6 e to the power x. Now, because negative 6 is less than, again, it's less than 0, we are going to have, again, a decay function. Now we have y equal to 2 to the times e to the power x. This will be exponential by double, so very quick. Then when we have y equal to e to the power x, it's exponential also, but not too fast. So for example, if I have y equal to 6, or let's say 7, times e to the power s, is going to grow exponentially very fast. So this is twice faster because 2 times e to the power x than y equal to e to the power x. So this gives us some concept about the properties of, again, exponential functions and their graph. Now from the graphs we saw that, again, if m is greater than 0, then the shape of the graph is still that of a growth function. But when m was less than 0, the shape becomes, again, is that of a growth function but turned upside down or refracted through x-axis, making the average y is less than 0. So in all cases, again, the asymptote is unchanged and is the negative x-axis in each case. The y-intercept is 0 and m, as we can see here. So let's go next to how we can model it with exponential functions. So many types of data, again, many types of data can be modeled using the exponential growth function. And the model here, we have exponential growth function, as we can see the graph increasing. This will be years passed from 1850. And we have a vertical value e, which gives us 85.53 e to the power 0.0309x. So this will be an exponential, or a model, which is an exponential model of some phenomena based on number of years. As the years increases, we see an increase. This concept can be applied to a population. So as we have noted, again, functions of this type have a special general form, which is y equal to c times a to the power x. First, a should be greater than 1. And exponential decay function have the general form of y equal to c times a to the power negative x, and also a should be greater than 1. Or as we said earlier, it can be y equal to c, b to the positive x exponent. But in this case, b have to be a value less than 1, but it should be positive. So b will be a value greater than 0, but less than 1. And that will give us also a decay function. So we have an example here. Historically, prices for goods and services arise, resulting in the erosion of purchasing power of $1. Now here we say with the $2012 as a reference, the 2016 purchasing power of 0.921 can be interpreted as meaning that in 2016, $1 with a purchase 92.1% of goods and services that could be purchased for $1 again in 2012. So here we see a decay. Now the table below shows the concept. So that gives us a purchasing power from 2012 to 2025. So the purchasing power of $1, 2012 was $1. But by 2014, it becomes 0.962. 2016 becomes 0.921, and it keeps going all the way to 2050. It becomes 0.362. So we can see the purchasing power is decreasing. So we have a decrease Now, is it decreasing exponentially? Most likely, but we have to, again, come up with the model. And this data, again, came from a Social Security Administration. And this is a projected purchasing power. Now, they say we should use this data. We start with the x equal to 0, which means we are starting from 2010, to find an exponential function that models the decay of the purchasing power of 2012. And also, what does the model predict as the purchasing power of $1 in 2028? And also, when will the purchasing power fall below 0.25? So if we have the data, this is a concept of almost statistics. If we have the data, we can come up with a model. And there are so many software applications that can make this very possible for us. So for example, if I'm using Excel, Microsoft Office Excel, we can use the scatter plot to plot the data. Now, when we plot the data, this is the shape that we get. Then we can right click on any of the point. Then we select the trend line. Then the trend line, we are going to see options to show the model, that is the graph, whether it's a linear, parabola, exponential. In this case, we're going to select exponential. Then show equation. Again, Excel will give us the equation. But again, using the function of the form a times x to the power x, the data can be modeled by the equation of this. Again, the best way to solve this problem is using an application, software application such as Excel or SPSS, etc. A statistics application. Also, we can use a calculator. Some scientific smart calculators also can do this calculation. So after we get the model, the rest is straightforward. Here they say show how the graph of the equation fits the line. Again, the software will do that for us. In this case, let's say we are using our calculator, such as a Texas Instrument 84 or 89 or 83 will do this work. Then to write this equation with a base greater than 1, we can write, here we have 0.9732 as 1 over 0.9732 to the power negative 1. So that will give us approximately 1.028 to the power negative 1. So we can say that this is a decay because the dollar purchasing power goes down as the years go by. Previously, we saw that our exponent is a positive variable for positive value. We can see from beginning, it's positive value, 0.9732 to the power x. Now we can change it to negative by getting this as a number, a whole number. A number should be greater than 1. And that's what we have here. So we have 0.128 to the power negative x. Again, is the same. Writing 0.9732 to the power x or 1.028 to the power negative x is the same. They are both the decay function. So we said this equation with the base greater than 1 will give us this. And that's what we have here. With the base less than 1 was the previously, it will give you 0.9732 to the power x, not to the power negative x. Now we should recall that we use an unrounded model in our calculation and also graph, unless otherwise instructed. So for example, we use s equal to 18 for the year 2028, and we can evaluate again the function. So if I, instead of the model is here. If I replace S with 18, I will get 0.66. So the purchasing power for 2028 will be 0.66. Same thing, evaluating from the graph or a table shows that the purchasing power falls below 0.25 when S equal to 553.8 or in the year 2064. If the model, again, the model remains valid. So this will be our conclusion for the beginning of our exponential function. And the next lectures, we're going to continue with the exponential function. So again, wish everybody the best. If you have any question, post it in a Blackboard or send an email. Thank you.